And so because my talk is the first talk of this series, I take the opportunity to tell a little bit of the background on green hydrogen production. Now, many of you know that green hydrogen is especially important for the hard-to-abate sectors, especially in the chemical industry. And so green hydrogen is particularly suited for green ammonium, green fertilizers, for making green steel as a reductant, and for making green methanol in the chemical industry, as well as for future energy storage. It has been projected that we will have 600 million tons of hydrogen in 2050, which is about $1 trillion. And so that's a lot of hydrogen, and we like to produce them for green hydrogen. Okay. The problem is that today, if you want to produce green hydrogen, even though we know it has a long-term potential of low to no CO2 emission, the price that you actually use to do it is about 5 times of the price of so-called gray hydrogen, which is to make hydrogen from natural gas. Of course, that comes with the price of CO2 emission, which is currently still for free. And so this is the reason why green hydrogen is not very widely used today. The good news is that according to a different analysis, eventually green hydrogen will undercut the so-called blue and gray hydrogens in all markets in the world. And so in this analysis, they look at the price of green hydrogen compared to other hydrogen, for instance, gray hydrogen. And of course, the price is different in different markets due to the electricity price, due to the local infrastructure, and so on. But according to this projection, at about 2035 or so, green hydrogen already start to undercut other forms of hydrogen, and well into the future, it will become that the green hydrogen will be competitive in terms of economics to other forms of hydrogen. Now, to reach here, obviously there are different assumptions. One assumption is that the electricity coming from renewable sources will be abundant and cheap, and this is actually happening today, and so less likely to even be better in the future. The other assumption is the capital cost. For instance, the electrolyzers need to have a radical decrease of cost. And so depending on, it doesn't matter where you're coming from, in which installations in Europe or in China, eventually current price of this electrolyzer had to come manifolds of decrease, okay, an exponential decay to make it compatible. Now, many of us working in this field understand that electrolyzers are actually quite large installations, and a radical decrease of such things really often means one thing, that you need to have a disruptive technology, otherwise it will not work. And we think actually here, the disruption by AEM technology is the way to make this thing happening. And so AEM technology is the one that many of us are working on in this ANEMEL network. And so I again introduce a little bit to you. Now, AEM electrolyzers actually will combine the strength of current technologies such as alkaline and PM technologies while avoiding the pitfalls. And in a very simple scheme, the specialty about AEM technology is that basically use anion exchange membrane to separate the anode and cathode sides of water splitting, meanwhile providing a mechanism to provide electricity conduction by hydroxide anion. Now, why is this so important? It's because if you use such a technology, you basically work in alkaline working conditions, and this is important because it's less corrosive, so it allows you to use base metals such as nickel, iron, steel, and so on as both catalysts and hardwares, and this will make it the whole thing inexpensive and scalable. Meanwhile, it's still a membrane technology, and what this is, without going into the detail, is that first of all, typically you have much lower resistance, okay, which will lead you to high current density, and that will mean that you have a small footprint to deliver the same amount of hydrogen. Also, it also will mean that you'll be compatible to intermittent energy resources such as wind and solar, which are the cheapest electricity possible in the future. And so they have these immense potentials. Then the question you ask is, why are we only hearing the developments today? And I will explain to you why that is the case. Now, first, let's look at from a simplest scheme. Let's say electrochemical cell for such electrolyzer. In this electrochemical cell, in the middle you have the membrane to separate it, and then you have two electrodes where you actually need catalysts to improve its efficiency. Okay, and so let's simplest cell structure for such a electrolyzer. And as I said, why is it not only now we are talking about AEM water electrolyzer? And this is because for many years, the central element, the membrane, is actually no good. Okay, and why is it no good? This is because it's actually really difficult to make it work. Now let me introduce a little bit about this membrane AEM. It's actually a really thin plastic, and typically is based on a polymer backbone with a linker to a cationic functional group. Okay, these cations then can interact with anions, so that's how it can transport the anion. The role of AEM will have two in this case. One is, of course, to transfer hydroxide, but also we need to transfer water between anode and cathode. The second thing it needs to do is to separate hydrogen and oxygen as a membrane. Now, in this case, there are many challenges on this membrane. First of all, it does not have sufficient conductivity, because conductivity is an important criteria for these energy devices, and this can be understood if we consider the molecular weight of this anion. Okay, now if we compare to a proton conducting material like nepheum, it's conducting solvated proton. Okay, now we know solvated hydroxide actually typically have effective molecular weight that is much higher, okay, than that of proton. So the diffusion coefficient by itself is already about half of the proton. That makes it that the conduction itself is less efficient. Not to mention the proton can sometimes go through tunneling. And so in this case, we know that nepheum, for instance, at 80 degrees can conduct with a conductivity number of 150 Siemens. While if you take the same nepheum backbone and you just transform it into a anion conducting moiety, and it immediately decreased to less than 50. And so that's not sufficient, and people typically think it will be more than 100 millisiemens. That is enough, okay? And so that's conductivity issue. The second problem is chemical stability, okay? Now, chemical stability is typically thought in terms of hydroxide because we are dealing with alkaline condition. Now, there are many reactions hydroxide can do because hydroxide, as chemists will understand, is a really good nucleophile, okay? And so if you take hydroxide, you do nucleophilic substitution. If your structure has a benzylic bond, and this is important because many of these polymer, in terms of for attaching this anionic group, you need a benzylic moiety. And for benzylic one, of course, you can actually do a substitution. You make a benzylic alcohol, so that's not really good. You can also do, if you have a group, alkyl group on the ammonia cation, you also replace it, and so you make, again, decrease anionic group. And you can also have this really specific for anion exchange membrane, which is called Hofmann elimination. That is better to your functional group. You have hydroxide attack, okay, then you make a basically an anionic group, and it's really good to release this anionic group in a neutral moiety and make a double bond. So that's Hofmann elimination. All this under high temperature hydroxide condition, that's less difficult. But also the polymer backbone has a problem. And previously people like to use aerial ether ones, and these plastic are really easy to get. However, in fact, hydroxide can attack and do replacement. Hydroxide can also attack quaternary carbons and so on. And so you basically cleave your backbone, and then you don't have your polymer anymore. And so chemical stability is a challenge. A third challenge is to do with how you use it in devices, because in devices we need actually mechanical stability. Now, typically we often call it also dimensional stability. The problem with dimensional stability is that when we need high conductive AEM, we typically need to have really high ion, okay, functional group. So the ion exchange capacity is high, you have high conductivity, but then you become really hydrophilic. You absorb a lot of water, and when you absorb a lot of water, you become a gel, and your mechanical stability just goes down, okay? And so that's a problem. So with all these three problems together, it's no wonder that for many years, people don't have the right membrane. And so in the last 5-6 years, people start to look at, a new generation of membrane. And one of them is this based on polyaryl piperidine, a PAP membrane. And this is actually pioneer work by a professor in Sweden, Patrick Janisch, and also a group in China. And so what they look at is this aryl ether-free polymer backbone, so pure hydrocarbons. So that's good for hydrolysis. And it has a robustic cationic group. I will explain to you why piperidine is robustic. And so because of this, in principle, they will have high chemical stability. And so one of the interesting parts is this piperidine, and I explain to you why. Because people have done systematic studies looking at all kinds of cations in accelerated tests, their lifetime. And so if you have a benzylic one, we already say it's not really good. If you have 5-member cyclic bonds, it's also not so good. Tetramethyl actually is quite not bad. But if you have a piperidine, okay, 6-member ring, and even this azu functionality, 2 6-member ring, is much more stable. And the reason for it is basically based on chemical structure consideration. So one of the major decomposition pathway is the Hofmann elimination, which is on the beta hydrogen, okay? And then you release it, and then you make a double bond. It turns out that such transition state typically is quite rigid, you have such a structure. However, if you make them into a cyclic structure, it's really difficult for them to trace it to get to the ideal transition state. And so you basically make it harder to do Hofmann elimination. And so based on these considerations, people have been working on this new generation of membranes. However, they are not really practical because these polymers are difficult to grow. And so if you know membrane chemistry or polymer chemistry, you know that actually to have a good membrane, you need a high molecular weight. And these ones, they actually cannot do it. And so then you cannot actually get a good membrane for use, right? And so how do we solve this? There are different approaches. And in our group, we have actually already we have 2 approaches. We basically think about it from a kind of architecture design, okay? To have high conductivity and mechanical stability. And this is done by Xile Hu, who was a PhD student in our group, and eventually he's now the CEO of our startup. And he has 2 approaches. One of them is by using branching. So you have polymer chains, you do a branch. This is good because with branching, you can typically get higher molecular weight. So you get a better membrane when you make it. But also branching somehow restrain the chain movement, so you reduce the swelling and increase the mechanical stability. In addition, typically when you make a 3-dimensional structure, we can control the morphology. You can actually create conductive channels, and so that's good for conductivity. And so this is, increasing both conductivity and stability. I think it also has a second approach that is taking advantage of sidechain engineering to make micro phase separation. And the idea is similar to nephium, that you actually have in your polymer a hydrophobic and hydrophilic part, okay? And this hydrophobic and hydrophilic part, they of course will do separation, and the hydrophilic part will basically facilitate hydroxide and water transport, while hydrophobic domain basically prevents swelling and make it stable. And so I will mostly talk about the branching approach. And so in this case, we have this. So this is one of the polymers that we make. So you can see that basically we use this phenotype species to make a branch structure. And with that, we have now we call it branium, a really good membrane. And in the lab, the way you make membrane is that you can use a simple weight coater. You dissolve the polymer solutions and you make the film and then you dry it. And you can see from this video that even in the lab scale, the membrane that we make mechanically is quite strong. we can compare our membrane properties to industrial standard or targets. And so I already mentioned certain things, for instance, conductivity or mechanical stability, which is typically called tensile strength or elongation and break. We talk about chemical stability, and the swelling ratio is related to mechanical stability, which is, and so on. And people can compare to Nafion as a benchmark. The U.S. Department of Energy also has certain targets, and this is our, I just mentioned our branch AEM. So in terms of conductivity, we have hydroxide conductivity more than 170 millisiemens. So this is really on the higher end, one can imagine. So in terms of conductivity, we are very good. In terms of swelling ratio, these ones are also not bad because it has hydrocarbons, aromatic ones. And in terms of tensile strength, we are also really high. And the elongation break, we are less elastic than Nafion, but we are again better than the DOE target. In terms of chemical stability, we have tested and we can extrapolate that from hydroxide stability point of view, it should be more than 30,000 hours because of our rigid and stable this functional group. Now we have the membrane, we also need other things. So we need catalysts, right? We need catalysts to make oxygen, we need catalysts to make hydrogen. And in our lab for many years of research, we also have those compounds available. And so I just mentioned that we have actually a new type of anode catalyst that from a turnover frequency number point of view is about 10 times of the classic nickel ion oxyhydroxide. And this was a work by Dr. Sung. And just to compare with classic nickel ion catalyst, if we compare them, we are in the lower over potential for similar current density, so we are much more active. We have studied using operantal X-ray absorption spectroscopy to the active structure of the catalyst. And this is typically done here. We are in collaboration with a group in Taiwan. We look at iron KH or nickel KH. We also look at X-depth and so on. And we know under OER conditions, our catalyst is basically two components, one iron oxide cluster in a corner shell into a nickel oxyhydroxide support. And this structure, I will draw it again here, is quite unique because here we have a bicomponent catalyst. This is different from the classic nickel iron catalyst, which is basically iron doped into a layers of nickel OOH, gamma nickel OOH structure. And we think this structure is giving some edge in terms of activity, and this can be understood by DFT calculations. And so our colleagues in our department on computational chemistry will look at iron catalyst. So if you have an iron, gamma iron OOH, this is not a really good catalyst, and everybody knows about it. Now this catalyst in our case is supported on gamma nickel OOH, and we know from iron to go to iron oxide, from iron to oxidation to iron oxo species, this is actually quite, according to calculation, quite easy. The difficult step is the hydroxide attack on the iron oxo to make iron OOH species. According to their calculation, in terms of energy itself, it's already too high, and then the release of oxygen is quite easy. And this is why everybody knows that pure iron is not a really good catalyst. However, in our case, we have a support on nickel OOH, and this is interesting because a lot of people already know nickel 2 to nickel 3 on nickel OOH is actually really facile. You can see by electrochemistry, this is about 1.3 eV, okay? And so this cycle is quite readily accessible. And so in this case, we have a scenario that we think that you have a cooperative catalysis where hydroxide first attack to iron oxo. This is very difficult, but it does not need to make a bond because the hydrogen here will be directly transferred to the nickel 3 oxo species as hydrogen atom transfer. So in one step, you basically do it together. So you make an iron oxo O2 species and nickel 2 hydroxide. And this decomposition to make iron catalyst again and oxygen and electron out is really easy. And so overall, according to calculation, it's again a really low energy at 1.3 eV. And so by having this cooperation, we go through this pathway, or the nickel OOH as a redox equivalent to take a hydrogen atom from the hydroxyl species, really promote this catalysis, and we have a really active catalyst. And so let's follow anode catalyst. Now look at the cathode catalyst, and this is one of the work in our ANEMEL project, that we have developed a nickel molybdenum catalyst that is comparable to platinum for high current density operation in AEM water electrolysis. So Ariana did this work. She developed these new particles that can do self-supported catalysts on a lot of different conductive substrates. And here I show you some activities loss. So there are different kind of previous nickel molybdenum catalysts, and the one that Ariana has is this color. Okay, it's AS1, Ariana Serban 1, and you can see that from linear swap voltammetry, the activity is already comparable to platinum or carbon. If we put it into electrolyzer, AEM electrolyzer at 1 amp, again, here platinum is slightly better, but we are also quite good. We can also do it at 3 amp, and again, it's quite similar to platinum in this kind of devices for the 50 hours. Again, we're trying to understand it by operando X-ray absorption spectroscopy as well as operando synchrotron XRD. And again, thanks to our friend in Taiwan, Hao Min Chen, we are able to do it. So here I show you some data. You can see that we compare to different kind of states under operando potential and to let's say reference compound that we know in terms of the compress, like catalyst is a nickel 4 molybdenum 4 in terms of the structure. We also look at XAS, so we look at both S structure, pre-edge as well as XZAP structure on both nickel and molybdenum, and so we are able to deduce its structure, and I will show you the structure. We found actually, typically when you make nickel molybdenum catalyst, this is why you have nickel 4 molybdenum, but in our case under operation, what we end up, due to our procedure, we end up a catalyst with a base of nickel 4 molybdenum, but on our surface we actually have excess molybdenum oxide. And this is really interesting because based on electrochemistry theory, water splitting in terms of water hydrogen evolution in alkaline conditions, you take water and you make a surface hydride, a surface hydrogen adsorbed species. And so once you make the surface absorption species, you can go through release hydrogen through different mechanisms. But the first step, in fact, is two steps. One is water dissociation, and then is hydrogen absorption. It turns out a lot of metals are good for hydrogen absorption, but they are not really good for water dissociation. So in alkaline conditions, for instance, platinum is 100 times less active than in acid because platinum cannot do water dissociation very well. But metal oxide, on the other hand, are known to promote it. And so we think in our case, we have molybdenum oxide that promote water dissociation. So then we basically have proton, okay? Then the proton will be taken by the metallic species to make absorb hydrogen species. And so from there, we make hydrogen. And so our structure is important for the observed activity in the sense that we do have, again, cooperative catalysis from metal oxides over a metal catalyst. And so if you use our membrane, you use our ionomer catalyst, you can actually do good things. And so in this case, we saw earlier this year, we can actually achieve AEM water electrolysis at 10 amp per square centimeter for 800 hours, okay? To demonstrate that the materials property now are ready, okay? We can actually do really, really incredibly difficult condition for this, okay? And so, as you can imagine, these materials are so good, so we decide to actually make a startup to actually transfer the technology and at least to make it something maybe useful, right? And so this is Noamia, who is also a partner in one of these projects, our Asterix, that we, our slogan is we create CPUs for green hydrogen production because all our materials are so critical. Just to show you that in the company, in fact, the most important thing is to scale up things. So we are able to scale up. This is our pilot production line for membrane synthesis. we have also been testing in kilowatt kind of stack to validate these materials. And so to show you some data, for instance, we have results to show that if we take even really thin membrane, 30 micrometer, and we test them on 5 to 5 cells, we test under our lab, we can do 3,000 hours, okay, still going, at 1 amp per square centimeter, to show that the property of this membrane is quite good. We also are continuously improving our catalyst. For instance, we recently saw a third generation of our OER catalyst, where we can actually do it at 60 degrees. We can achieve 1 amp at 1.65 volt. And if we like a good number, and we typically like to have a high number, so we take high heating value of hydrogen. And so if you calculate the energy efficiency, that is actually 90% energy efficiency. And this is real efficiency, obviously. And so we need to increase it from 70 hours to 70,000 hours, obviously. But we think that it demonstrates that what AEM water electrolysis can do. In fact, such as I suggest actually to myself, that I don't think there's any fundamental limitation in terms of AEM electrolysis compared to PEM electrolysis. And we also can be really proudly say, people often criticize water electrolysis being not energy efficient, but 90% efficiency is not something really low, right? So anyway, I also like to show you that our material are not only just validated by ourselves. I show you some client data. This is one client that shows that they've been doing differential pressure 35 bar, so dry cathode 35 bar, and they found our membrane has passed the hydrogen crossover test. Okay, and this is a real test, so I think really important, because in real electrolysis you want to do a dry cathode high pressure, because a lot of energy in compression of hydrogen is wasted in the first 30 bar, in fact, and so that's important. We also have one client that tested our material membrane especially for 1 year, and we run it for 1 year, and it has stable but also importantly intermittent operation at ambient conditions. And the way they do it, they sometimes decide, okay, I will do Monday to Friday, okay, continuous, or I will start it off, or I will do 8 hours per day and then I start it off, and all these kind of things. Okay, this is a good mimic for intermittent kind of study, but and so on. And they don't control the temperature, so you can see the voltage can be high and low depending on it's summer or winter, and if they control the room temperature or not. But the main point is that this thing has been run for a year and it's still working, and we're really happy about that. We also have another client using their really their materials in terms of electrodes, their configuration. The thing I mainly want to show is that this is a kilowatt stack, and whatever they do, I don't know what they do, but what we know is it's running for 1,000 hours, and the membrane is doing its job. It never get broken. Okay, and so that is on this scale. And so then I will do some publicity for you. So in our company, of course, we have the membranes and associated polymers. We also have the anode and cathode that I just mentioned to you. We also use our ionomer for people who like to use platinum. But we also have tools that, because of our experience, we made electrochemical cell ourselves. They're really good. You get good numbers and good publications if you want, because they are actually not corrosive and all this. So we have tests, we solve a lot of problems. We also have made ourselves testing stands, and they actually really good for organizing in the lab. And last news, we're really happy. We are now doing a beta test. We actually using our materials. We work with developers. We can make hydrogen generator. Okay, completely PFAS free. We can do it for up to 500 milliliter per minute, which means it's enough for a lot of applications in the lab. Up to 150 volt, and you can up to 8 bar. Okay, and for the feed, even though it's AEM, all you need is to use deionized water, because we have a system where it's weekly basic in stock anyway. And so we're still testing this, but just to say that we have reached a step where we can have a product for your day-to-day use if you want. Of course, this is a baby step towards megawatt style, but I think we're really happy to be here. So with that, so let's for the company part, we can be your partner for green hydrogen production. And I would like to thank the people who done the work. This is my research group in the lab, okay. And so we have this is current year. Of course, a lot of work has been done by previous group members. This is Ariana, part of your ANEMEL project. Here is the company team. So we have Xingyu, who I think once joined one of your activities, but in any case, is a former student in my group, but now is a CEO of the company. We have different team members. I think Alex is with you here, and so feel free to talk to him. And so with this, I'd like to conclude my talk. I'd like to thank you for your attention.